Okay. So let's kind of continue where we left off last time. So we had been talking about functions. So in section 1.1, we defined what a function was, right? And talked about how to tell if something was a function or not based on the representation of that function. And in section 2, we talked about domains and ranges and how to find the domain and range of some functions. And we talked about a couple of different techniques that we could use to do that, right? Today, we're going to start talking about some properties of functions, or some, maybe I should say like adjectives for functions. So these are some properties that functions can have, or some ways to describe them, right? So if you define something, you want to be able to build up a vocabulary so you can talk about and compare and contrast two of those things, right? Like if you have two flowers, it'd be like, oh, this flower's petals are blue, and this flower's petals are red, and this flower is this tall, and this flower is that tall, and you want to be able to have a language to compare and contrast them, right? That's what we're going to be doing here over the next couple lessons, is kind of build out a language to kind of compare and contrast two different functions. Okay? So this section 1.3 is about continuity. So we say a function is continuous if you can draw the graph of the function without having to pick up your pencil. Is kind of a silly way to describe a continuous function. But most of the things that you saw last year and previous would be continuous functions. So like a line would be a continuous function, right? You can just draw that without having to pick up your pencil. Or, like a quadratic would be a continuous function. You can draw it by just without having to pick up your pencil. Or like a square root function. Oops. Or you can draw it without having to pick up your pencil. But there was one type of function you studied last year that sometimes you can't draw without picking up your pencil. Anybody want to venture a guess as to what that would have been? You would have studied it last year in your Algebra 3-4 class. Rational function is correct. Very good. So let's say we have something like y equals 1 over, well, let's do x minus 1. So remember, rational functions often, but not always, have a vertical asymptote where the denominator is 0. So here the denominator is 0 at x equals 1, so we'd have a vertical asymptote there. And then we'd have like a horizontal asymptote in this case at y equals 0. I can tell it's going to be y equals 0 because this is a simple rational function. It's of the form like a over x minus h plus k. And I remember the value for h is the vertical asymptote, and the value for k is the horizontal asymptote. The horizontal asymptote in this case doesn't matter too much. We really just care about the vertical one. But if I went and drew the graph, then I'd have that part, and I definitely have to pick up my pencil to draw that part now, right? I can't do the both arms. Can't draw both arms of the graph without having to pick up my pencil and go to a new spot. Yes, of course. Is everybody okay with the difference between something that's continuous and not continuous? It turns out there's actually 3 different types of discontinuity. One of them you're familiar with is called the infinite discontinuity. So this is things like a vertical asymptote in a rational function. Is an example. We call these guys infinite discontinuities. So let's say this is the point or the vertical line x equals h. We call these an infinite discontinuity because as the graph approaches h, the y value is heading towards either positive or negative infinity. You guys can kind of see that? That when you get close to that asymptote, either the graph shoots off to positive infinity or shoots down to negative infinity. That's why we call it an infinite discontinuity. Keep in mind, not all vertical asymptotes are discontinuities, though. What's an example of a function you studied last year that had a vertical asymptote where it wasn't discontinuous? Starts with an L. A logarithmic function, right? You remember logarithmic functions have a vertical asymptote, but they would be continuous because I can draw that whole logarithmic function without having to pick up my pencil, right? The asymptote doesn't break it up into 2 different sections. Do you guys remember that now? Okay. So the next 2 types of discontinuity you may or may not have remembered. One of them you could have talked about last year. Kind of depends on the year, who your teacher was. I know when I teach the honors algebra 3-4 class, I talk about this, but not everybody talks about this. It's called the removable discontinuity. So if you had seen this before, this is something that can happen with rational functions. So let's show you the case where that can happen. So let's say we have a rational function that looks like this. So we have x plus 2 over x squared plus 5x plus 6. One of the things that you can do with rational functions is on occasion, they can be reduced, right? To reduce a rational function, what do you have to do first? You have to factor, right? Everybody remember that? Okay. So in this case, there's no factoring that we can do to the numerator because it's just a linear term. But the denominator we can factor to x plus 2 times x plus 3. Notice the x plus 2 terms, or factors, are in common between the numerator and denominator. So we can reduce those out. And we can say that's just the same thing as 1 over x plus 3. You guys remember doing things like that last year now? Okay. Now, what we've written here, though, is not technically correct. What is the problem with what I've written here? If these two things are truly equal, I should be able to pick any value for x, plug it in, and get the same result. Correct? What if I plug in -2 to this one? Well, I'm going to get 0 over 0. If I plug in -2 to this one, I'm going to get 1 over 1. Are those two the same? No. So at least one value, they differ. Why? What is special about -2? It's what caused the piece that we crossed out to become 0. So in fact, these two that I've circled in yellow give you the same y value at every point except at -2. Where on the right it gave us 1, and on the left it's undefined. So to make sure they agree, what we have to do is, with our answer here, add in the caveat that x can't equal -2. You okay there? So if I tried to graph this, I'm going to have my vertical asymptote at -3. I'll have my horizontal asymptote at 0. Before -3, I'll just have my normal rational function. But at -2, I don't have a point. So we'll just put like an open circle to represent that. This is your removable discontinuity. It's just basically a hole in your graph. So it's just like a single missing point where the graph goes to here and then skips a beat and keeps on going. So it's not like an asymptote where it shoots off to positive or negative infinity. It's just like a little gap in your graph. Did you guys talk about this last year when you talked about rational functions? It's okay if you say no, but if you did, let me know and okay. That's good. Okay. Do we feel okay here? You remember now removable discontinuity a little bit after we jog some memories? You remember doing this? Okay. That's good. The last type of discontinuity we've seen is called a jump discontinuity, and this is one that you probably haven't ever seen before. And that's okay. So the most common place where we get a jump discontinuity is when we're using like a piecewise function. So for a piecewise function, what we do is it basically is defined in two different pieces. So maybe my graph acts like 2x plus 3 when x is greater than 1. Let's say less than 1. And then it acts like negative negative 2x minus 1 when x is greater than or equal to 1. So what the graph of this is going to look like is, for this part, everywhere before 1, it's going to look like that graph with slope 2 and y-intercept of 3. But there is no point at x equals 1. That's why I've drawn the open circle there, just like with our removable discontinuity. And then I'm going to draw the other part of our graph, which starts at 1, but acts like -2 or x minus 1. So it'd look like this. So we call this a jump discontinuity because it's literally like the function just jumps up or down from wherever it was going. You know, you imagine like walking along the function and whoop, we jump down and do something different. So we call that a jump discontinuity. Okay. In general, my expectation from you guys would be that if you looked at a graph of something, you'd be able to pick out which one it was, or identify where the different discontinuities were, just from a picture. I wouldn't expect you to find these things algebraically or anything like that. But I wanted to like connect these to like back to things you'd seen before, right? Or I wanted to like show you where it comes from in mathematics. In the case of the jump discontinuity, which you've probably not seen before. But that's it for continuity. All I really want you to be able to do is be able to look at those pictures and tell if there's a discontinuity or not from the picture. The next section is about increasing and decreasing functions. Do you remember talking about this last year? Yes, of course. Did you talk about increasing and decreasing last year? I ask you this over and over again because it just helps me know like how much detail do I really need to do? Am I reviewing or am I doing it from scratch? If these are things that I know you've done before, we'll go and do this a little bit more conversationally, a little less formally. If these are things you've never seen before, that's a different story. My suspicion is that you have. So what we mean by increasing and decreasing is if I have a function and you pretend you're like the miniature version of yourself and you're walking along that function going from left to right, uphill is increasing, downhill is decreasing, flat is constant. That's basically what we mean. Now there's a very formal definition of like what we mean by increasing or decreasing or constant. Basically it would be like an interval is increasing if for every point on that interval the slope between those 2 points is positive. If it's decreasing, the slope would always be negative, and if it's flat, the slope would always be 0. Or if it's constant, I guess would always be 0. Is that okay with you guys? So the idea here would be to we're going to look at the picture and be able to describe the intervals where the graph is behaving either as increasing or constant or decreasing. So let's just do a little example on this. Okay. Okay. So, the idea here, we're going to write down the intervals where the graph is increasing, where it's decreasing, and where it's constant. So I'm just going to start by just identifying the parts of the graph that are increasing. So I'm going to imagine that there's the miniature version of myself. I'm going to start on the far left-hand side of the graph and just walk along the graph. So when I do that, this section is increasing, right? So I'm going to ask myself, okay, what is the smallest x coordinate on that section of the graph that's increasing? Well, that section of the graph includes the arrow that's pointing to the left. So the smallest x value then is -infinity. And because it's an infinity, I know it automatically gets a parenthesis. Everybody's okay with that? And what's the biggest x value of that section of the graph that's increasing? -1. Now here's the general rule for if you have a transition point. So if you have a point where the graph changes from increasing to decreasing or constant, if you have a point where it's changing, those points aren't ever included. Okay? So when we do increasing, decreasing, and constant, the endpoints of the graph are never going to get included, or the endpoints of the section are never included. The reason that is, if you take that endpoint and you compare it, there's nothing to compare it to. There's no other point to the right of it to compare with it to figure out a slope for it that's still increasing. The point to the right of it would be, in this case, constant. So it doesn't really make sense to deal with it that way. All right, let's look for a section of the graph that's constant. I see one right there, right? So what is the smallest x value from that section of the graph? -1. And the biggest? 2. And again, because these are transition points at the ends there, they're never included. And then let's identify the constant section of the graph, which is right there. I'm sorry, what? I'm sorry, not const. Yes, thank you. I put them in the wrong spot here, guys. Thank you. My mistake. I said everything right. I just put them in the wrong spot. You ever make a mistake? It happened to me. So for the decreasing part, what's my smallest x? 2. And my biggest x? 5. And again, we get parentheses all the way through. And again, if we're looking to be extra clear, we should probably say that these are x values, because here it's not entirely clear. We didn't ask for just a domain or a range. So should probably put x's there just to be clear. What if instead we gave you, instead of giving you a picture, what if we gave you an equation? So we'll call this guy example A, this guy we call example B. What would I do here? Would make this easier. If I had a graph, right? Can you graph something like this? I have a calculator. Makes it really easy to graph something like this. That's what I would do. Just because it's for the notes, I'm going to use Graphmatica to generate this graph because it's easier to embed that image into the notes with this program than it is with the calculator emulator. But you don't really need to do that if you're you don't need to do that if you're just doing like your homework or whatever. I'm just doing this because it's notes. So there's my graph, right? Boy, that makes life a lot easier. So increasing, decreasing, constant. How many sections do you see that are increasing? I see 2. I see this section that is going uphill. And I see this section that's going uphill. Do you guys agree with that? There's no other sections that are going uphill though, right? So because I have 2 separate sections, that means I'm going to need 2 separate intervals, right? Okay. So the first interval begins with what x value? Negative infinity. Excellent. And then if I look here, this first interval is going to the vertical asymptote, right? If I look again here, what is the vertical asymptote got to be? Yeah, -3 and +3, right? Everybody agree with that? Do I have to show you why that is, or are we good with just stating it? I'd hope after last year it was pretty clear just by stating it, but if we needed to show it, we can show it. Again, it's the first week of school. Like, I'm not expecting you guys to be like as sharp as you possibly can be on your math stuff, but you know, if we don't need to, let's not. Okay, so that's going from -infinity to -3, right? And then we'll go to the next section. Where does that next section start at? -3. And where does it end at? 0. Very good. Questions on how I did that? And they both get parentheses, right? Because one is starting at the asymptote and the other is like a transition. How many decreasing sections do you guys see? 2, right? This one and this one. Okay, so the first section starts at, how about 0? Right, starts there. And it ends at 3. And again, those are either one end is a transition, the other end's at an asymptote, so they're both going to get parentheses. And the next section starts at 3 and ends at +infinity. And again, both of those get parentheses because one end is an asymptote and one end is an infinity. So, is everybody okay there? Okay. So, once you have a graph, it should be pretty easy to do the increasing and decreasing pieces. Yes? That would be my suggestion. Make a graph. Okay? Along with increasing and decreasing, we should talk about the term extrema. So extrema is a generic term. There are 2 types of extrema. There's the maximum and there's a minimum. So the extreme are basically the extreme points on the graph, like the very highest or the very lowest. I'm going to actually erase this because we're going to put something underneath this. So we have one type of extreme is the maximum. So the maximum of a function is a value f of c such or that is greater than or equal to all other range values of f on some interval containing c. There's actually two types of maximums. There is local and there is global. So a local maximum means there could be others or other maxima that are, I shouldn't say maxima, we should just say other points that are higher. And a global means there are no other points that are higher. So just as a quick little example here, how many maxima do we see on this one? Should be just 2 maxima. There's 3 extrema, but there's only 2 maxima, right? So, if I look at the maxima here on the right, is this local or global? It's global, right? That's the highest point of the entire thing. The point or the maximum on the left is just a local because it's only the highest point in its little neighborhood here, right? If you go look at the entire graph, there are points higher than that, though. Is that okay? Difference between local and global? Is there a situation where there's no global maximums? Sure. What if I have a situation like this? How many maxima do you see? 1. And this is just a local. Why? Yeah, you have all this stuff going up forever that contain points that are higher than that maximum, right? Did you guys do this last year? Okay, good. All right. So then we have minimum which is the exact same definition as the maximum, except instead of less than or equal to, it's greater than or equal to, right? Thank you, OneNote, for saving me all that writing. How'd you like that for some sneaky snuff? Again, there's two types, local and global. I'm not going to rewrite the definitions again because those definitions are basically the same. We're just going to do some examples, especially since you talked about this last year, right? Okay, how many minima are in this one? 2. There's one right here and one right here. The one on the left is local, and the one on the right is global. Can there be a situation where you have no global minima? Of course, right? The same kind of situation that we saw before. Where we have example here, we have one minimum, and it is only local because there are lots of points lower than it. Everybody feel okay on this? Do you remember using your graphing calculator to find these points? Some say yes, some say no. Let's review it again, okay? While we have a few minutes. Let's just say we have the function x squared minus 4. And we want to find any local or any maximums or minimums, okay? First thing we know is that we got to, if we're going to talk about the graph of something, we have to type it into the y equals menu if we're going to graph it, which we've already done. Everybody okay there? Now I need to graph this. Usually, as far as a window goes, I usually start by doing zoom and then standard, because that'll just put me on the window -10 to +10 on the x's, -10 to +10 on the y's. And I can always adjust from there, but that's usually a good starting spot. Everybody's okay with that? So if I look at my graph, I've identified one minimum here. Everybody agree? To find exactly what that point is, I can press the second button and then the trace button and pick the minimum command. So you can either scroll down and press enter, or because it's command 3, you can just press the number 3. That's what I'm going to do. Now the calculator is going to ask us a couple of questions. It's going to ask us left bound, right bound, and maybe guess. I don't remember for sure. We'll find out in a second. For left bound, it just wants you to pick a point that's left of the minimum you're looking for. So my cursor is right here. I can just use the left arrow on my calculator. That's somewhere left of it. So I'll press enter. Notice now the question has changed. It now wants a right bound. So I'll just move to the right of that minimum. I don't know, that looks good. And press enter. It does want to guess. The guess doesn't really matter. Anywhere in between those two values you picked is fine. Moving closer to the point would actually let the calculator find that minimum faster. But I'll tell you what, it's going to take you longer to move your cursor than it would the extra compute cycles for the calculator to find that minimum. So it's really of no benefit to move any closer. You can just press enter again on the guess. And there's what it tells me. So that says the minimum is 1.84 capital E to the -6, and y is at -4. What the heck do I interpret this as? Interpret it as 0, right? What does that capital E mean? That's scientific notation, right? So this is 1.84 times 10 to the negative 6th. So it's 0.0000184. Or negative 0.0000184. Oops, one more 0 there. Either way, what's that number really close to? 0, right? This is just an approximation error on your calculator from doing this. Is everybody okay there? So make sure you see the E's there, because that makes a big difference to interpret that as 0. Okay. We'll start the next section a little bit. We probably won't have time to finish, but that's okay. The next section is about symmetry. There are 3 types of symmetry. You can have symmetry with respect to, that's WRT, is just me abbreviating with respect to, the x-axis. So what does that look like? If I have a graph like this, is symmetric to the x-axis, because it looks like one half of it is just the reflection of the other across the x-axis. Is everybody okay with that idea? And it's easy to visually see that, right? So that's what the graphical is, but algebraically, what does this mean? So if I think about, yes, sir.
Like reflection across that set.
Yeah. What does that mean algebraically? So that means, say, for this point, this could be the point like 1, 1, right? So I would also need the point 1, negative 1. Everybody agree with that? And if this is the point like 3, 2, this then would have to be the point 3, negative 2, right? Everybody agree with that? So the y-coordinates kind of must be opposite of each other, right? So the y-coordinates are like my x comma f of x's, right? So if this is x, the y-coordinate would be f of x, and this would be x comma negative f of x. Everybody agree with that? So this is telling me that if I have the y-coordinate f of x, I also should have the y-coordinate negative f of x. So for example, if negative f of x is equal to negative 3, and I do negative of negative 3, I get 3. Right, I get the positive 1 back. That's all we're saying. So we can have symmetry with respect to the y-axis. that would look like this, right? Where the one side of the graph is just the reflection of the other across the y-axis. Everybody's okay there? Visually speaking. Let's think about the same way now algebraically. So like if this is the point -1, 1, then over here this has to be the point +1, 1. If this is the point like -2, 4, this would have to be the point +2, 4. If this is the point -x, f of x, this would have to be the point x, comma, f of x. So what this is saying then is that f of -x has to give me the same answer as f of x. Right? If I take f of 3, or I'm sorry, f of -2, I get 4. If I take f of +2, I also get 4. Right? No matter what value of x I put in, whether it's positive or negative, I get the same y coordinate back out of it. Functions that are symmetric across or with the y-axis are also called even functions. Should mention that before we move on. And the last one, we have symmetry with respect to the origin. Actually, we should be more specific. Let's say this is a 180-degree point symmetry with respect to the origin. Now that's a wordy way of saying this. But basically all this is saying is that you do both a reflection across the x and a reflection across the y. So if I take this half of my graph and I reflect it across, say, the x-axis first, I get something like this, right? Everybody agree with that? And then if I take that piece in green and I reflect it across the y-axis afterwards, I'd get the other half of my graph. So 180-degree point symmetry with respect to the origin is basically the same as a reflection across the x and then a reflection across the y, or you could do the other order. You could reflect across the y and then across the x. Is everybody okay with that idea? As visually what we're looking for? Algebraically, what are we saying here? So if this is the point -1, 1, this would have to be the point +1, 1, right? If this is the point -x, f of x, this one would have to be the point x, comma, f of x. So what we're saying here is that f of -x equals negative f of x. Right? That if I take -x, f of -x is -1, which is the same as negative f of x. Right? Oops. These guys are also called odd functions. That 180-degree point symmetry. Okay, so if I want to prove a function is odd, even, or neither, for even, I need that f of negative x is equal to f of x. For odd, I'd need f of negative x is equal to negative f of x, right? Those were the algebraic interpretations that we used. So that's what I'm going to do here. So I'm going to start with negative, or f of negative x. And I'm going to see if I get f of x, negative f of x, or neither one of those two things. So if I plug negative x in for x, I replace all the x's in my function with a negative x. Negative x to the fourth power, though, is just x to the fourth power, right? Because 4 negatives make an even, or make a positive. Everybody agree with that? Which is exactly what f of x is. So I can conclude then this is even. Because I've shown that f of negative x is equal to f of x. Let's do another. This is probably the trickiest thing in chapter 1. Just saying. Let's say we have g of x equals 2x cubed plus 3x. So I'm going to start with g of negative x. So everywhere there was an x, I'm going to replace it with a negative x. So I have 2 to the negative x, or 2 times negative x to the third, plus 3 times negative x. Negative x to the third is negative x to the third, right? And then times 2 gives me negative 2x to the third. Everybody's okay there? 3 times negative x is negative 3x. And I notice that both of these are negative. If I factor that negative 1 off, I have exactly g of x, right? Oops. So I have negative g of x. And this is odd. Is everybody okay there? Let's do one more. So h of negative x. Again, taking all the x's and replacing them with negative x's. Negative x squared is just x squared, so 4 times x squared is x squared. Negative 3 times negative x is positive 3x. And then 9 just stays 9. So I notice that this is not equal to h of x, right? What's the difference? The sign on the 3x, right? Okay, well, maybe could it be equal to negative f of x? What if I factor a negative sign out? Is that going to equal negative f of x? No, right? So the signs over here again are wrong because the sign on the 4x squared and the 9 are wrong. So this was not equal to h of x. And then this is not equal to negative h of x. So we conclude this is neither. A little hint as a self-check right after announcements or prayer.
Let's stop everything and call upon our God, the Father, the Son, and the Holy Spirit. Amen. Is there a person or people or an intention that I would like to lift up to God in prayer right now? May the God of peace dwell in our hearts now and always. In the name of the Father, and of the Son.
Wait 1 second here, guys.
Amen.
I just want to tell you this one self-check because it's useful.
If you turned in a parking application and your last name starts with an A through M, you could stop by the office after school. And again, out in the parking lot, please keep distance and keep your masks on and don't throw masks in the parking
Okay,
lot.
1 second though, guys, 1 second. So if my function is a polynomial, all three of these were polynomials, right? If the degree of all the terms, this is a degree 4 term, this is a degree 0 term, if all the degrees are even, you're going to have an even function. If all the degrees are odd, this is a degree 1 term, degree 3 term, and a degree 1 term, you're going to have an odd. If they're not all the same degree, then it's going to be neither. A degree 2, a degree 1, a degree 0. This one was neither. So that's a nice little self-check. If we're proving that does not work, but it tells you at least what you're trying to prove, what the answer should be.